Hello dear students. Welcome to the world of nuclear technology, scientific breakthroughs, and sustainable development. My name is Maria Tserina, and I'm a leading specialist at the Mathematical Modeling and Digitalization departments of Prariv JSC. The Prariv, or Breakthrough Project, creates the future of nuclear energy. And that's what we are going to talk about today. I will also tell you how to look into that future. No, not with magic crystal balls or spells, but through science and technologies. But before we travel into the future, let's look at the present. What nuclear energy looks like today. Modern nuclear power plants provide humanity with clean, stable, and affordable energy. Nuclear energy doesn't depend on the weather. It operates in various climatic conditions. One of its main advantages is the enormous energy density of fuel. Just imagine, 1 gram of uranium gives as much energy as about 2.5 tons of coal. During operation, a nuclear power plant does not emit greenhouse gases into the atmosphere, and over its entire life cycle, from uranium mining to waste disposal, a nuclear power plant CO2 emissions are lower than from solar panels or wind turbines. But even such significant advantages over other energy sources do not mean that nuclear energy should rest on its laurels. On the contrary, its huge potential requires constant progress. Today, the industry faces a few natural barriers that it must overcome on its path to a bright future. The reserves of natural uranium-235, which fuels thermal reactors, are not infinite. According to various estimates, it will last for 60 to 150 years at current consumption levels. Therefore, we need to find a way to expand the resource base. For example, to use the much more common but less active isotope uranium-238 as a fuel. The Prariv project is the answer to these challenges. Its goal is to create a new generation of nuclear energy based on the principles of inherent safety and competitiveness. The main idea is a closed nuclear fuel cycle with fast neutron reactors. More than 2,000 specialists from over 60 organizations are working on the Prariv project. The project is currently in the active implementation stage. In Seversk, Tomsk region, a pilot demonstration energy complex is being built. This complex will demonstrate the closure of the nuclear fuel cycle. Now, let's pause for a moment and talk about nuclear fuel cycles. There are two types of such cycles, open and closed. The auto arc in the diagram shows the open nuclear fuel cycle, the traditional chain from uranium mining to spent fuel storage. The inner circle with green arrows shows the closure of the fuel cycle. Unlike the open cycle, here spent nuclear fuel is not sent for long-term disposal, but is reprocessed to extract valuable fissile materials, which are then reused to produce new nuclear fuel. Radioactive waste is minimized and the resource base becomes almost limitless. Fast neutron reactors can produce new fuel not only for themselves, but, if necessary, also for thermal reactors, and can also burn uranium from spent fuel left by their thermal elder brothers. This is called a dual-component nuclear power system. The closed nuclear fuel cycle has many advantages. First, it's a new level of safety. The very design of fast neutron reactors reduces the risk of accident to a record low. Second, it provides technological support for the nuclear non-proliferation regime. Third, it makes full use of the energy potential of uranium, and it's economically feasible. A closed cycle makes nuclear energy truly sustainable and virtually waste-free. This is not science fiction. It's an engineering reality that the Prarif project is creating today. At the very beginning, I promised to tell you how to look into the future. And now we come to the most interesting part. How can we be sure that a complex technological system will operate reliably and securely even before its actual launch? How can we see a potential problem long before it might occur? The answer is digital twins. A digital twin is not just a beautiful three-dimensional model. It is a virtual representation of a real-world object, system, or process. Digital twin is updated with real-time data, which can be used for machine learning and reasoning to make better decisions. We can study all sorts of potential situations, analyze performance problems, and create potential enhancements that can be used to improve the real physical object. Digital twins are designed around a two-way flow of information that occurs when the object sensors provide relevant data to the digital twin, and then that happens again when the insights created by the digital twin are shared back with the original source object. And since digital twins are meant to mirror a product's entire life cycle, it's not surprising that digital twins have become widely used in all stages of manufacturing, getting product from the design stage to the finished product and all the steps in between. Prarif is using digital twins to look into the project's future. Now, let's take a look at it. This is the Pilot Demonstration Energy Complex. It consists of three main parts. The first is the spent fuel reprocessing module. The second is the fabrication refabrication module, where fresh fuel is made from reprocessed materials. And the heart of the complex is the reactor unit called REST. This is a fast neutron reactor with lead coolant, one of the safest and most promising in the world. All parts of the complex operate together on the same site for the first time in history. The digital twin of the Pilot Demonstration Energy Complex consists of databases, computer, mathematical, and simulation models, as well as design documentation, requirements, and real-time data. Since the digital twin evolves in parallel with the physical object, the fabrication refabrication module currently demonstrates the highest level of maturity among all components of the digital twin. By the time the construction of the complex is completed and the power unit produces its first portion of energy, its digital twin will have already prevented equipment failures, saved millions of dollars, and become a new global standard. The Prarif project is not just a step forward, it's a leap into a new era of nuclear energy. Safe, efficient, and virtually waste-free. Thank you for your kind attention.
Dear friends, good afternoon. My name is Yuri Sestunov. I am the Chief Technology Deputy of the Composite Division of Rosatom. My educational background is composites, and my work is related to the creation and implementation of the composite materials and technologies. Today, I will tell you what composites are, where they are used, and why these materials are opening up new opportunities in aviation, space, energy, and construction. State Atomic Energy Corporation is actively developing new business areas beyond its core nuclear energy production and technology chain projects in nuclear medicine, wind energy, additive manufacturing. One of Rosatom's key strategic priorities is the introduction of advanced materials and cutting-edge technological solutions based on carbon fiber. Today, Rosatom Composite Division comprises 17 manufacturing plants and its own advanced research center, which develops new materials, including those based on carbon and glass fiber. We don't simply produce composites, we are creating the technological foundation for Rosatom's future products in new industries for corporation. Today, based on independently developed technologies, the production of advanced composite materials and fibers meeting the highest global standards has been launched. Domestic technologies for advanced materials and fibers, matching the best international counterparts, have been developed. However, we face ambitious goals, scaling up production and entering international markets. We want to join the group of global technological leaders in the composite industry. Carbon fiber is believed to have been synthesized by Thomas Edison in 1879, while he was working on the light bulb. The modern era of composites began when scientists developed plastics. Before that, the only sources of adhesive and binders were natural resins delivered from plants and animals. In the early 90s, plastics such as vinyl, polystyrene, phenol, and polyester were developed. These new synthetic materials outperformed conventional naturally delivered resins. However, plastics alone could not provide sufficient strength for certain structural components. Reinforcement was required to provide additional strength and stiffness. Engineers soon realized that composites offered not only lightness and strength. For example, fiberglass composites were found to be transparent to radio waves, and soon this material was used to protect electronic equipment. In the 1970s, the carbon fiber that we know today was developed. Today, it is almost impossible to imagine any industry where composite materials are not used. Composite materials, or simply a composite, is a material consisting of two or more components, each with different physical and chemical properties. When combined, they create a new material or improve the properties of one of them. The properties of composite materials depend mainly on the physical and mechanical properties of the components. The matrix gives the composite its shape and monolithic structure. The properties of matrix determine the material's performance characteristics: operating temperature, density, specific strength, fatigue resistance, environmental resistance. Reinforcement fillers are introduced into composite materials to increase strength, stiffness, and plasticity, as well as to modify electrophysical and thermophysical properties into different directions. There are many different types of composite materials. The diversity comes from different factors. The reinforcing filler in the structure of composite can be arranged randomly or oriented. Oriented reinforcement fillers are classified into unidirectional or two-directional. The most widely used composite materials in engineering are those reinforced with high strength and high modulus continuous fibers. Polymer matrix composites based on thermosetting, epoxy or polyester, or thermoplastic can be reinforced with glass, which is called fiberglass composite, or carbon fiber reinforced with plaster, organic or inorganic fibers. Also, metal matrix composites do exist based on aluminum, magnesium, copper, titanium, or nickel alloys, reinforced with boron, carbon, or silicon carbide fibers. Carbon-carbon composites consist of carbon matrix, which is reinforced with carbon fibers. Ceramic matrix composites reinforced with carbon, silicon carbide, and other heat-resistant fibers. The comparison between composite materials and traditional or classical materials brings us to the main advantages of composites: high specific strength and stiffness, or specific models of elasticity, corrosion resistance, fatigue resistance. Let's talk a little about carbon fiber. Today, there are three main types of raw materials for the industrial manufacturing of carbon fiber. The first is PAF, polyacrylonitrile. Second is pitch, petroleum or from coil. Pitch-based carbon fibers usually have a high modulus of elasticity. However, this fiber is quite expensive and its manufacturing process is very labor intensive. Rain-based carbon fiber has lower properties, but some very specific applications. Carbon fiber manufacturing process is multi-stage. It consists of several steps. First step, we take white fiber, PAN, and treat it with the high temperature from 200 degrees to 300 degrees in the air atmosphere. At this stage, we get intermolecular cross-linking and fiber becomes black. After this stage, fiber is not melty. On the next step, we treat fiber with a very high temperature up to 1500 degrees. At this stage, we call carbonization. At this stage, all the rest atoms leave the fiber and we get carbon fiber itself. Carbon fibers are used to make fabrics and prepregs. A separate category of materials, prepregs, semi-finished product where the reinforcing filler is pre-impregnated with a binder. The most common types of binders used in prepregs are the epoxy resins. Because of epoxy resin used to make prepreg is living material, it is not cross-linked. We have to keep the prepregs with the low temperature up to minus 18 degrees centigrade. The advantages of composites are widely used in various high-tech sectors of global industry, increasing the competitiveness of finished products. In nuclear, hydrogen, wind energy, development today is simply impossible without composites. Modern high-speed trains, electric vehicles, fuel, gas, and hydrogen tanks for transportation are impossible without composites. Here I would like to highlight three main directions of the industry development. First, getting digital twins of composites and digital twins of the composite technologies. Second is recycling. And third is reducing the cost of carbon fiber and the cost of carbon fiber conversion technologies. According to the experts, the next step in the composites will be driven by reduction of the price for carbon fiber and the price of the carbon fiber technologies 10 to 20%. This slide shows some interesting facts about composites. Just I would like to say that composites, especially based on carbon fiber, is the next step for the space exploration. Spacecrafts and space technologies building in space is not possible without carbon fiber and without composites. So what is the future of composites? First, I would like to underline that composite technologies, materials for composites, will become friendly. Composite technologies must become faster. Carbon fiber must become less expensive. The technologies of manufacturing must be more accessible. A day will come when composite technologies will be as affordable as the home 3D printing now. I wish that if you go into the technical development, sooner or later you will do something for composite development as well. I wish you good luck and have a good trip. I wish you good luck and have a good trip.
The edge of the world beneath the Ursa Major. This famous northern constellation served as a guide for the ancient Greeks, pointing the way to the north. The Arctic is both a harsh and an astonishing place that has long captured the human imagination of sailors, poets, travelers, and scientists. To this day, it remains alluring and still not fully explored. In recent years, we have witnessed the Arctic becoming increasingly integrated into the global economy, thanks to its resource potential and the development of new international transport corridors. Today, we will explore this remarkable region and learn about the contribution that the State Atomic Energy Corporation Rosatom is making to its development. Before I begin, I would like you to take a mindful moment and think, what associations does the word Arctic bring to your mind? What do you see? Most likely, polar bears, ice, snow, and cold have just appeared before your eyes. Am I right? The Arctic is indeed very often imagined as an icy desert, but in reality, the Arctic is a vast, economically strong region with a population of around 4 million people. Its territory includes the fringes of North America and Eurasia, the Arctic Ocean with its islands, and the adjacent parts of the Atlantic and Pacific Oceans. The total area of the Arctic is more than 20 million square kilometers. The Russian part of the Arctic region accounts for nearly a third of the entire Arctic shelf, stretching from Franz Josef Land to Wrangel Island. You have likely heard about the harsh climate of the Arctic, and it's not a surprise. Winter temperatures here drop to minus 50 degrees Celsius, while summers are short and cool. The Arctic experiences polar days and nights, the northern lights, and is home to remarkable plants and animals found nowhere else on Earth. Musk oxen, bighorn sheep, polar bears, killer whales, and beluga whales. Furthermore, the Arctic shapes the climate of the entire planet, acting as a natural air conditioner and preventing the continents from overheating. Thanks to the diversity of minerals found beneath the soil of the Arctic, the region is often called the world's freezer. The Arctic landscape is filled with rich deposits of natural resources, many of which are critical for the transition to renewable energy, ensuring a clean future for the planet and generations to come. These include, for example, lithium, nickel, cobalt, manganese, and graphite, essential for energy storage systems, metallurgical silicon for microchips, and rare earth metals for electric vehicles and wind turbines. In addition, the Arctic holds lots of other valuable resources, from construction materials such as sand, gravel, and crushed stone to precious stones such as diamonds and rubies. It is fair to say that today, not only global economic development, but also the planet's energy security would be unimaginable without the Arctic valuable resources. For Russia, the Arctic zone makes up nearly 1/3 of its territory. To be precise, 28%. The geography itself, including the country's unique territorial expanse, has historically pushed Russia northward, overcoming natural challenges. So how did people learn about the existence of the Arctic? As early as the 11th century, the Pomors, one of the oldest ethnic communities in Northern Europe, living on the northwestern shores of Russia, were exploring the northern seas, hunting, and establishing the first trade routes. In the 18th century, the Great Northern Expedition, led by Vitus Bering and Simon Chelyuskin, created a map of the Arctic coast of Russia for the first time. In the 20th century, the USSR made a breakthrough, building the world's first nuclear-powered icebreaker, completing through voyages along the Northern Sea route and launching drifting stations such as North Pole 1. Today, Russia continues to study the Arctic using satellites, underwater drones, and new scientific stations, helping to unlock the region's socio-economic potential. From the Pomors to high technology, the Arctic remains a territory of discovery. What is the NSR and why is it important? The Northern Sea route runs along the coastline of Russia through the seas of the Arctic Ocean. It is one of the most discussed projects in the context of global logistics. It is the shortest sea route between Europe and Asia, with a length of about 5,600 kilometers. The history of Russian exploration of the Northern Sea Route spans more than 500 years and begins with the earliest voyages of the Pomors through these waters, as mentioned earlier. Building on their experience, in 1525, the Russian diplomat Dmitry Gerasimov proposed the practical use of this route and created the first project of the Northern Sea Route, as well as the first map of the coasts of the Arctic Ocean and Muscovy. Muscovy being the political and geographical name for the Russian state used from the 15th to the early 18th century. What are the advantages of the Northern Sea Route? The NSR has numerous advantages. In particular, it is the shortest sea route between Europe and Asia. By significantly reducing the distance between Asia to Europe, the NSR helps carriers optimize cargo transportation costs while allowing us to receive goods as quickly as possible. The NSR runs only within Russian borders, which ensures complete stability and predictability of cargo flows. This route has global significance, reducing congestion in the world's logistics system. The NSR also helps relieve currently overcrowded transport channels, avoiding queues and accidents. When passing through the Northern Sea Route, there is also no risk of piracy, making the NSR a safe and efficient addition to existing shipping routes. Furthermore, the reduced distance offered by the Arctic route contributes to lower CO2 emissions. It also stimulates the development of Russia's northern regions, creates new jobs, and promotes the adoption of green technologies in shipping. The Northern Sea Route is the transport artery of the future, connecting the economies of Europe and Asia through the Russian Arctic. For most of the year, the seas of the Arctic Ocean are covered with ice. But how is navigation through ice even possible? The answer: nuclear icebreaker fleet. Russia is the only country in the world to possess a nuclear icebreaker fleet. The fleet is operated by Rosatom. Rosatom issues permits for passage along the NSR, helps chart safe routes through the ice, and escorts vessels during navigation. The primary purpose of nuclear icebreakers is to ensure the escort of ships along the Northern Sea Route. Thanks to their powerful reactors, the latest project 2220 nuclear icebreakers can break through ice up to 3 meters thick. The use of a nuclear reactor allows icebreakers to operate for up to 7 years without refueling. And most importantly, nuclear icebreakers provide virtually no carbon dioxide emissions, making them environmentally safe. In addition to cargo transportation, Russian nuclear icebreakers take part in expeditions, are sometimes involved in rescue operations, and even carry tourists. A nuclear icebreaker possesses several features that enable it to force its way through the Arctic ice and guide vessels behind it. An ultra-strong hull design, great weight, and powerful reactors. Nuclear icebreakers advance through the ice by essentially leaning their bow onto the ice surface. The ice barrier breaks under the icebreaker's weight, and the ice fragments scatter to the sides, creating a channel for the passage of both the nuclear-powered vessel and the ship it is escorting. The icebreaker's hull is extremely strong and is made of steel capable of withstanding low temperatures. In addition to a powerful hull, nuclear icebreakers are equipped with nuclear reactors. To put it simply, its working principle can be described as follows. The nuclear reactor produces steam. The steam drives turbines connected to generators that produce electricity. The electricity, in turn, drives the propellers. It is important to note that the operation of a nuclear icebreaker does not cause atmospheric heating or heating of seawater. The energy of a nuclear icebreaker is directly solely at breaking the ice. As of today, the nuclear icebreaker fleet consists of 8 nuclear icebreakers, with another 4 at various stages of construction. As I have already mentioned, nuclear icebreakers have 3 main advantages: efficiency, safety, and autonomy. The crew of the most modern Project 2220 nuclear icebreaker is about 50 people. To ensure the crew's comfort during voyages, the newest icebreakers even have a swimming pool, a gym, and a cinema. They are truly floating mini-cities. Now, I invite you to look at the journey that our icebreakers have made and draw inspiration from their path. We will look at 3 projects that symbolize past, present, and future. December 3rd, 1959 is considered the birth date of the nuclear icebreaker fleet. On that day, the flag was raised on the world's first nuclear-powered icebreaker, Lenin. This event gave rise to the nuclear icebreaker fleet development and unlocked the transportation potential of the Northern Sea route. The 8 nuclear icebreakers in Russia's fleet have incorporated and multiplied all the advantages of the world's first nuclear icebreaker. The icebreaker Lenin had a power output of 44,000 horsepower, significantly higher than its predecessors, the diesel-powered icebreakers. I would like to ask you to remember this number because we will need it later. At the same time, Lenin's fuel consumption was very low. While a vessel powered by diesel fuel had only enough supplies for a month, the nuclear-powered Lenin could operate on average up to 4 years without refueling. Lenin operated for 30 years and escorted 3,741 vessels. Today, you can see the founder of the nuclear icebreaker fleet at the seaport of Murmansk, where it serves as a museum. Now, I would like to move to the present and introduce you to the newest and most powerful icebreakers of 22220 project. They already have a power output over 81,000 horsepower. Do you remember the number I asked you to recall from the previous slide? The icebreaker Lenin had about 40,000 horsepower, so modern icebreakers are already twice as powerful. In addition to being able to break through ice up to 3 meters thick and create a channel through ice up to 4 meters wide, these icebreakers are universal. The use of variable draft allows icebreakers of this design to operate equally, effectively both in open seas and in shallow waters at the mouths of polar rivers. Finally, we move to the project that represents the future of Arctic development, Project Rossiya, which will have a power output over 160,000 horsepower, twice that of the most powerful modern icebreaker. It will be capable of breaking through ice up to 4 meters thick and creating channel through ice 50 meters wide. The Rossiya-class nuclear icebreaker is the flagship of the future Arctic fleet, representing a true technological breakthrough in the exploration of the Arctic. Let us summarize. First, the Arctic is one of the most interesting and promising regions on Earth for exploration. It is where technologies and innovations that shape the future of the entire world are born. Second, the Northern Sea route, the shortest transport route connecting Europe and Asia, running through the seas of the Arctic Ocean, is confidently becoming part of global logistics. Third, safe and efficient navigation in northern seas is made possible by nuclear icebreakers, and Russia possesses unique technologies and experience in operating in the far north. If you, like me, can't wait to experience the Arctic beauty we have talked so much about, I invite you to join me in watching a short video at the conclusion of our excursion.